Hello everyone. The title of the invention is a method for automatically selecting process parameters for an additive manufacturing process. The inventors for the invention are Professor Mayank Goswami and Sunita Khod from the Department of Physics, IIT Roorkee. So let us start with the introduction of additive manufacturing process. It is a process of creating three-dimensional object from a CAD model by depositing the material on the bed in a layer by layer manner. So what happens is that uh, firstly we CAD design the sample which we want to 3D print, and then we convert it into an STL file and import it into the slicing software. In the slicing software, the process parameters are set by the operator, and then this and then converted it into the G code file. This G code file contains the information about the movement of the extruder. The extruder of the 3D printer moves as per the instructions provided in the G code file to 3D print the sample. The the sample is then 3D printed by the nozzle of the 3D printer. And what happens is that the 3D printed sample may not be the exact and may deviate from the actual CAD design. Thus, the quality of the 3D printed sample depends upon the process parameters which are set. So these parameters are decided by the operator. So in order to improve the quality of the 3D printed sample, we can first vary the process parameter, assess the quality, and then we can repeat the process iteratively until the quality of the sample is satisfactory. However, with experience, the operator may gain enough experience to reduce these iterations. Yet, it is a costly and time consuming approach. Thus, there's the quality SSAM process where a operator is involved consists of three stages. Firstly is in selecting the process parameter. Second is in assessing the quality of the 3D printed sample in assessing the first decision, and then iteratively changing the decision A if the quality is not satisfactory. However, with experience C or iteratively changing the decision A is not required. What we can do is that one solution is then using the artificial intelligence method. Artificial intelligence methods may augment and phase out the manual experience, avoid the manual error, and then fasten the AM process. The involvement of AI methods also saves the environment by printing the sample non-iteratively. Therefore, we are proposing a novel invention in which two AI models are integrated in a series pipeline. These two AI models are trained with the entity data. First is AI model 1, which is trained with the entity data obtained from CT scanning the 3D printed sample. Second is the AI model 2, which is used for process parameter selection. It is trained with the set of process parameter and the quantitative value of defects, which can be any structural parameter such as surface roughness, porosity. In our case, the structural parameter used is porosity. So we have CAD modeled the sample in the SolidWorks and then 3D printed these samples. We have varied the process parameters to vary the quality of the 3D printed sample. Layer height and nozzle speed are varied. Layer height is varied from 50 to 70 micron. Nozzle speed is varied from 30 to 80 mm per second. And then we have created the G code file and then 3D printed the samples. In all, 38 3D printed samples are 3D printed from different process parameters and different 3D printers installed at the tinkering lab in the institute facility. Also, we have printed one sample sample by the human perception. What we did is that we asked the operator at the tinkering lab to set the process parameter and print the sample according to his experience. The process parameter which he set are 200 micron layer height, 80 mm per second nozzle speed, 100% infill density, and lines are the infill pattern in the sample set by the human perception. And then all these 3D printed samples are CT scan using X-ray CT lab, using X-ray CT system installed in our lab for the NDT data collection. The 3D volumetric data of different samples printed from different printers is as shown in the figure. And then this NDT data obtained from scanning the samples is used to train the AI model 1, which is a unit model containing 23 layers. The training accuracy of the trained AI model is found to be 98% for the different samples printed from the different printers. And then the segmented ROI segmented data obtained from this AI model 1 is used for the quantification of the structural parameter, that is the porosity. And then the AI model 2 is fed with the set of process parameters and the quantitative value of porosity, and then this is trained. The training accuracy of AI model 2 is found to be 82%. However, validation accuracy is found to be 93%. And then the optimal process parameter predicted by this trained AI model is found to be 55 micron layer height, 30 mm per second nozzle speed, 100% in infill density, and grid is the infill pattern. The porosity in this sample, as estimated by AI, is found to be 0.139%. However, we compared it to the sample which is set by the human perception or an experienced operator. The process parameters which are set by the experienced operator are 200 micron layer height, 80 mm per second nozzle speed, 100% infill density. Lines are the infill pattern. The porosity in this sample as set by the human perception by the human operator is 2.68%, which is very much higher than the set by the our AI model 2 or the proposed methodology of the our invention. So we can say that the samples 3D printed by the proposed methodology are better in terms of quality assessment. Thank you.